All right, hello, Fruitport High School AP Chemistry students. So if you're watching this video in order, you should be watching this video after our lesson. We learned about valence shell electron pair repulsion theory, VSEPR, and we did the hybridizations of SP, SP2, and SP3. Those are the highest priority for learning in class and AP test. And so those are the ones we did in class. This video will do sp3d, and then I'll make a second video on sp3d2 hybridized compounds. And those videos are less important, so if I'm not in the room helping you, you're learning from a video, that's okay. But there'll still be some homework questions and Kappa questions on there. So you have your packet with notes, and I'm just going to go through them really quickly and show you some 3D pictures with the camera, okay? So if we were to get a sample molecule that can actually squeeze 5 atoms across the central atom, here's an example. We have phosphorus with 5 atoms, 5 fluorine atoms, and if we were in a hurry, we would go over how to make the Lewis structure, but here's our Lewis structure with 5 bonds and 0 lone pairs. And anytime we have 5 bonds and 0 lone pairs, we have this phenomenon, right? We have a hybridization of sp3d. So we took one s orbital, 3 p orbitals, and a d orbital. You'll notice s, 3 p's, and a d add up to 5 because there's 5 species around the phosphorus atom. To spread this out, we actually get this shape here, all right? So if I kind of rotate this molecule here, you'll see there's 5. And to me, it looks like this. We have a north pole and a south pole and 3 across the equator. And between an equator atom and a pole atom, the bond angles are 90 degrees. But if I rotate it this way, you can maybe see around the equator, they're all 120 degrees. That's why our notes have 2 different bond angles. My attempt to draw it 3-dimensionally with one phosphorus coming out and one phosphorus going back and trying to label which angles are 120 degrees. This angle would be 120. From this fluorine to this fluorine would be 20. They're on the equator. We got a north pole and a south pole that are 90 degrees. One way we sometimes draw this is the pinwheel model. And if we were to draw this, this would be a phosphorus here. And we would have a fluorine, a fluorine, a fluorine, a fluorine, and fluorine. I can put those on there. Phosphorus here, fluorine, 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 fluorine. This is another representation of a pin going through a piece of paper. By the way, these molecules are so spread out, there is no dipole. There is not a polar molecule. Okay? The shape for this we call a triangle bipyramid. So if I could use this kit to show this here, I don't know if you can kind of see this or not, but we have this compound that has got a pyramid on the top and a pyramid on the bottom. So we got this triangle base here right across the equator with the pyramid pointing up and a pyramid pointing down. And I'm not sure how great this model is on video, but you'll see it in class when I see you next. Okay? Now, our second page of notes that we have here, we're going to substitute in a Lewis structure that has 4 bonds off the central atom and 2 extra dots, an unbonded lone pair. So there are still 5 things. There's fluorine, 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 and a lone pair. And so the hybridization is still sp3d. And again, it's not 90-degree angles because we have an interesting 2-dimensional phenomenon. All right. So when we take a look at this molecule, we have to take off a bond. Is there more room off the poles or more room off the equator? Well, the answer is there's more room off the equator to remove an electron because remember, lone pairs want as much space as possible. The shape of this is so unscientific, we actually call it a teeter-totter seesaw. I don't know if you can imagine that I'm kind of flipping back and forth like a little kid's toy, but this is called a seesaw shape. I can't believe that that's the official name when we have so many, more scientific sounding things. We still have the same bond angles, and this one would be polar. If you could imagine this here, the two fluorines I'm holding are opposite and would cancel each other, but these two are bent, so they don't cancel each other. I'd probably have a little bit of a charged pole over here and a charged pole over here, okay? All right, if we kept going and we had our next one of sp3d, we would need an example with 3 bonds and 2 lone pairs. IF3 does that for us. So we have 3 bonds and 2 lone pairs. That's still 1, 2, 3, 4, 5 things on the central atom. So it's still sp3d. Some people put the D in front. They call it dsp3. That's the same thing, by the way. And so I would take another bond off the equator where there's space. And this shape is called a T shape because if you rotate it like this, we have a T shape. Okay? Oh, I forgot to show you my models. This is what the seesaw shape was for the other one. And you can see it kind of seesaws back and forth like the other one. But 3 bonds, or 4 bonds, and then I got the 2 green dots to represent a lone pair. This is sometimes called a distorted tetrahedron or a seesaw. And a T-shape is planar. So a T-shape looks like this. We have a lone pair and another lone pair off the central atom spread out. And because it's a flat molecule, we call it planar. One more to go in this video, and that is, what if you have 2 bonds and 3 lone pairs? XEF2 would make that if we made the Lewis structure. We'd have 2 bonds and 3 lone pairs. And this one here, again, remember we built it off of the original molecule here that had, I lost a hydrogen. Let me find one. Our little trigonal bipyramid. And if we take 3 bonds off the equator where there's extra room for the electrons, we get this shape, which is right back to what we had earlier. We have a linear shape, 180 degrees, and it's not polar. And so this linear one looks a little bit similar, but you'll notice that we have 3 sets of orange dots on the equator to show that there's room. They take up space, but we physically can't see them. Because they're not, with an atom with a nucleus. All right, there is a video with a kind of trying to do some notes. Remember when we do this, make the Lewis structure accurately, and then either check the notes or think about, what if I had 2 fluorines and 3 lone pairs? How would they try to spread out around the xenon? And then we can start to answer all of the criteria. Okay.